Okay, hello. Today we're gonna do a FizzBuzz exercise using IntelliJ IDEA and Java and test-driven development, and we're gonna do some refactoring. So FizzBuzz is a kind of converter where we put n and we get the same number converted to string as a result. But if the number is dividable by 3, then we get the fizz string, and if it's divisible by 5 we get the buzz string, and if it's divisible by 3 and 5 at the same time, we get FizzBuzz. So that's basically the whole algorithm, and we're gonna do this using a technique called triangulation, which is that we add some tests for a given case, and we generalize when we have at least 2 examples. I will show you how we do that in practice. Here we have the infinite test, which we will use to run our tests. Okay, so let me just add a simple test class called FizzBuzz specification, and we'll add a single test, and we say that FizzBuzz should convert input to expected value. The name is kind of a silly one, but we'll do this test as a parameterized test, so some of the details will be in the parameters of this method. Anyway, let's import this class and make sure whether the test run works. So we can see that we have the assertion error, and it says not finished yet, so our environment works. And we will use something called JUnit params. Oh, here it is. Okay, and let's add a parameters here, and just to make sure that this works, because the JUnit params lets us to basically create parameterized tests. So let's say 1, 1, and the parameters will end up here. Let's leave it as this, because we are still trying out whether our test environment works. Input equal to input. This is still a test. Oops. That's not what I meant. Let's try again. Okay, the test should pass, and it does. which by the way is pretty much obvious because I forget about this. And when I put 2 here, the test should fail, and it does. So yeah, we have basically got our environment working. So now let's start with the first test case, which says that the 1 as integer should be converted to 1 as string. So let's say this. Let's remove this assertion, and let's name the main class algorithm, or FizzBuzz algorithm. Okay, and we say that when we get result, and by the way, this is not an output but an expected output. When we get a result or output, we can use this name now. Input, then we should be able to say that, assert that output equal to expected output. So that's basically what we are trying to achieve. Now we have some classes and methods that don't exist, and what we do is to use the intention actions and just create that class, and we did, and it's here. And by the way, we need to have this method, so we do the same. We create method, and we leave this for now. Okay. So now we're failing with unsupported operation exceptions. What we need to do is to have this test failing on this line, on the assertion. So let me just say that I'm returning null. And now we can see that we have the assertion error, and it's this line. So now that we have the test failing for the right reason, we can get to actually implementing the logic. And as I said, we are doing triangulation, which means that we use as naive in output or logic as possible, and we say that we return 1. And the test passes. So we now have green bar and nothing to refactor because we don't have anything yet to generalize. So we need to add another case. And the next case will be of the same kind, because previously we said that 1 as int is converted to 1 as string. And okay, so what we need to do now is to insert the brackets here, as we are using an array. And we can see that the next test case failed because we expected 2 but got 1. And this is because we are returning 1 always from this method. So let's just say that if input equals 2, return 2. If input equals 1, return 1, and let's just say that we are returning null at the end. And yeah, the test passed. So now as we look at this code, we see some kind of repetitive structure. We see some kind of pattern, and now we can generalize. So the first thing we can spot is that this is actually a stringified version of 2. So we can say string value of 2, and the same applies here. And we can see that the tests still pass. So now we can see that this is the same as this one, and this one is the same as this. So we can, and both are the same as input. So we can just say input, and add this one here. By the way, we can add input here and add it here, and it still passes, but this if statement doesn't make any sense. And the same applies here, and this is not needed, and this is not needed as well, so we end up with this. So that was the generalization applied to the triangulated parts of the code. Now let's add some cases for fizz. So we say that, for example, for 3, we should get fizz. And again, let's add the simplest implementation that can work. If input equals to 3, then return fizz, right? We need this if statement, because if we didn't use it, we would get compile error, and the previous test would not work. So again, let's copy this and use another value that would give us fizz, which is 6. And we've got another test failing. So let's go here and say if input equals 6, then return fizz. And again, we can see that the tests are passing, and we got another duplication, right? The code is the same here and here, and the only thing that's different is this. So both of these values are examples of a number that is divisible by 3. So let's just say that we did this, and the tests are still passing. So let's do this, because that's the example of the same rule, and the tests are still passing, and now we've got a duplicated code, and we don't need one of those ifs. So we've got this. Okay, and let's do the same for the bus. Bus was to be divisible by 5. So this is what we are currently doing. And I will rush a bit with the implementation, because this is exactly the same kind of work as previously. Sorry. Okay, and it should pass. Now we need 10 because 10 is the next number that is divisible by 5. And again, so again we have this duplication, and let's eliminate it the same way as previously. Because both of these constants that we used previously were examples of a number that is divisible by 5. So now we don't need this one. And the last thing we've got is FizzBuzz. And FizzBuzz was to be returned for the numbers that are divisible by 3 and 5 at the same time. So the first of such numbers is 15. And for 15 we expect FizzBuzz. And as you see, the test fails. So I'll add FizzBuzz just the same as the previous numbers, but I'll try to make one mistake here. So let's say I rush too much and I add this if statement here. Okay, and you can see that it didn't help the test to pass because I made the mistake of putting this thing at the end before, not after 5 and 3. And everything that's divisible by 15 is divisible by either by 5 or 3, so none of the values will actually get here. It will be caught by either here or here. And as you can see, we expected FizzBuzz but got buzz, so we ended up here with R15. So what I need to do is to take this thing and move it to the top. So now the test passes. And I can take another number which is 30 and do exactly the same thing. So here I say 30 and it passes again. So now we have two examples and we can generalize like this. And 30 is also divisible by 15. So I'll do this. And I don't need one of those. Yes, and now I'm finished with the simple, easy implementation of FizzBuzz. But actually I want to do much more. I want to use this example as an excuse to show you how a series of if statements can evolve into a chain of responsibility. And actually what we have been doing so far was to spot duplication and eliminate it by generalization. And as you see here, here and here, we have another kind of duplication, but in the structure. So each of the if statements is in the form of if predicate, then generate, right? And the same here and here. So maybe we can generalize and have a class with two methods, like this one, and introduce a class for each of those if statements and run them in a loop or recursion. Let's see what we end up with. So the first thing I want to do is to extract these things as methods. So let's say this is FizzBuzz, and this would be translate to FizzBuzz. And by the way, this should be lowercase. Okay, and we can do exactly the same thing here. And this was buzz, so we can name it is buzz. And we can do exactly the same here. So let's extract method and call it translate to buzz. And this one, which is the fizz case, so we say is fizz, and we say translate to fizz. And this one is a little bit weird because it seems not to fit this structure, but actually it does. Let me just write and let's do this. If true, okay, so now we can just no, we can't use this, not implemented exception. Oh, we can use this one, never mind. So you can see that the structure is similar here and here. So let's do exactly the same thing as for the previous if statements and say is default, and here let's say translate to default. Okay, so now we've got a bunch of private methods, and you see that they come in pairs. So let's try to put each pair into a separate class. So for this we can use the extract delegate refactoring and say for example this one and this one, and move them to the default translation class. Okay, so now we can see that we are using this field that is defined here, and this new class has both of these values. And we'll do exactly the same with the rest of the methods. So now fizz. let's call it Fizz translation, and not this one. Okay, and this one, this will be a bus translation. Refactor, and this one will be called FizzBuzz translation. Okay, so we've got a bunch of fields with new classes and a lot of methods that are actually not needed. We can just select them all and remove them. Okay. So now we have this pretty set of if statements with each of these if statements in its own class, and we can try to create a subclass for all of these classes, or an interface that we will call translation. But to do that, we would need to ensure that the signatures of the methods are exactly the same, and we can see that the names are different, and that here we pass an input parameter and here we don't. And likewise we pass an input here and we don't do that here. So we need to fix that. The first thing we'll do is to pass the input here, pass it here, and add it as a first parameter. And we need to add the input here. As you can see, the input is not used, but it will let us unify the signatures of these methods. So the next thing we need to do is to unify the names. So let's say the predicate will be named is applicable, or is applicable to. And this method will just be called translate. By the way, you can see that the tests are still passing, so we are protected with our changes. Okay. Now we can try to go to one of those classes and try to extract an interface. But this will not work now because the methods are not public, and they need to be public to be able to extract an interface. So let's go here and here and make all of these methods public. So now we can try again to extract an interface. Let's say that we do it for this class. So let's choose both. Let's name the interface translation, and let's refactor. Okay, the IntelliJ asks me whether I want to use translation here instead of bus translation, and I will agree, because why would I refuse? So now we've got our interface with two methods, translate and is applicable to, and we can apply this interface to the rest of the translations. So this one implements translation, this one does not. Let me just copy this. And as you can see, adding the interface implementation didn't force us to change anything in this class. So this is what we were trying to achieve with this refactoring, and with unifying the names and the input arguments. Okay, and the last one is like this. Okay, so now that I did this, I can actually remove this, and this. So now I have just a bunch of translations. And what I would like to do is to transform it into a chain of responsibility. And to do that, we need to spot one nice thing, because this is an if, and if we say else, this is still a valid structure. And the chain of responsibility is recursive, so we would like to have the recursive structure visible here. So let's do this trick. Here, here, and here. So now you can see that we have this structure. If something, then return something, else do the next thing. If something, return something, else do the next thing. If something, return something, else do the next thing. If something, return something, else do the next thing. So this is the chain structure that we were looking for. So now we can get right to creating new classes that will make up the chain. So for example, let me say that this is new invalid chain element, or maybe we can do this differently. Let's extract methods and say translate. Okay, and let's extract this to a new class by choosing extract delegate, translate, and let's call it invalid chain element, because we are creating chain elements now. And let's refactor. Okay, so we can see that we have this chain element that has the translate method. And actually, let's make it public. And by the way, we need to pass the input here, because we want the method to be the same for all the cases. So yeah, now we've got what we wanted, and we can extract a new interface, which I will name chain element, because this would be the element of a chain of responsibility, and refactor. Okay. Okay, so we have a first chain element that is assigned an invalid chain element, and we can make this thing a new chain element. Okay, so let's try to extract a method. Like this, and we'll call it translate again. So now we have this thing, which I would like to extract as parameter. Like this, and the invalid chain element as well. So let's do this. Now let's call it, well, let's leave it as it is. Now we can take this method and extract delegate, which we will call chain element with next. And let's try to refactor it. Okay, so now we've got a new chain element with next, and it's invoked like this. But actually, I don't want these arguments in the method. I want them in the constructor. So I will do inline, and I'm back with the object here. So let me just do this. And change the signature. And by the way, I want to assign this to fields, so that I have two fields, translation and chain element. And I want this to be the field, and this one as well, and this one. So now you can see that I don't need this argument, and I can safely delete it. And I don't need this one. And by the way, this name is not too good, because I will call it just translation, and this one. And this one is actually next chain element. Yeah, so now we've got the chain element with next, which has the current translation and the next chain element. And we can say, if translation is applicable, then apply translation, which, by the way, let's call it like this. else next chain element translate input. So this is the structure that we can build a chain responsibility from. Now let's get back to the algorithm. And we can see that this is another chain element with next, but the next translation being the Fizz translation, or sorry, the current translation being the Fizz translation. So I can say, for example, new chain element with next Fizz translation, oh, I can't do this yet. So let's see what stops me. Okay. I forgot to make this thing implement the interface, and by the way, this should be public. And we're all good now. We can say again, new chain element with next Fizz translation, and let's see. Yeah, it passes. So let's just see whether we can just delete this thing. And yeah, we can. And here we've got exactly the same structure. This is another chain element with next, and the next chain element is this one. So let's just say that this is new chain element with next, and this is the bus translation. So let's invoke it with the bus translation, and yeah, like this. By the way, this is the next chain element, and this is translate. And I believe we don't need this and this. Yeah, I was right. Again, we have the chain element, so let's just format this thing a bit and say that we want new chain element with next, and this one is FizzBuzz translation, and the next element is all the rest up to here. So I'm closing this, and the test still pass, and I believe I don't need this and this. And I need the return value. So yeah, what I currently have is the chain of responsibility structure, and I can actually inline all these other translations so that I have all of this in one place. Okay. And it looks a bit like a mess, actually. But what we can do is to extract all of it as field, initialize it in the constructor, rename it, and we can do another thing which is we can take this and we can have it injectable as a dependency by introducing a parameter like this. Sorry. Removing this and this. And now it's all in our test, which is not that great, by the way. Anyway, we can extract it to a separate method. And move this to production code because it's a composition root, but we don't have production code. Actually, we don't have the main method, so we can move it nowhere. So we'll leave it here. Anyway, it still looks like a mess. Before we clean it up, we can do one more thing. Because if you look at FizzBuzz translation, it's actually Fizz plus buzz, and this one is sorry. Actually, the fizz case was for 3, and this buzz case was for 5. And by the way, this was N, not R. Okay. So now we can actually view this FizzBuzz translation as a composition of both fizz and buzz. So let's just say new buzz translation applied to input. New fizz translation applied to input. And we can extract these as fields, so we can do this. Constructor, yes. And let's rename it to translation 1, because when we look at it, we don't need it to be a fizz translation. And we can extract this too. And let's rename it to translation 2. And we don't need it to be a buzz translation as well. So here we can say translation 1 is applicable to input. And the test still passed. And here we can say translation 2 is applicable to input. Okay. So now we can take these two things and inject them using interfaces and constructor. So let's do this. And let's inject it like this. And do exactly the same thing with the second translation. And the test should still pass. And yes, they do. And by the way, we don't need this, and we don't need this. So now actually this translation has nothing to do with fizz or buzz, because it knows only the translation interface. So we can just change the name to something like some translation. Yeah, so we have eliminated another redundancy. And let's look at this method, and it became even more ugly. But actually it has one nice property. We are composing our behaviors on the object level. So actually we have a mechanism for modifying the behavior of the application by modifying the composition of objects. And let's see if we can make it a little bit more readable. So let's extract some methods like this one, and let's call it fail. Let's extract this to a method called convert to string. Oh, sorry. Yeah. Let's extract this method, and let's call it translate to Fizz. Okay, and this one as well. Oh, sorry, not method object, but method translate to buzz. Okay, so now we have this sum translation, and we can extract this as well by saying both and going there, extracting again as parameters. I know this looks crazy, but bear with me. And this one. So now it says both translate to Fizz and translate to buzz. And now rename it to try Fizz, or even apply Fizz, apply buzz. So it still looks a bit ugly, especially because of this, the chain element. So let's try to do something with this, and let's call it then. Again, extract these parameters. And call it next. Okay, so we've got this then, and let's try to reuse it here. Okay, it doesn't look too good, but we can sort it out somehow. we can copy this method and sorry, not like this, and say try to, and this one we can rename to else try to, and this is else fail. So now we have the FizzBuzz algorithm, and actually we can do even more. We can extract method again, like this, and we can say with input integer extract this again as parameter, okay. So now we say with input integer try to both apply fizz and apply buzz, else try to apply buzz, else try to apply fizz, else try to convert to string, else fail. So we have created some kind of mini language, because we can here say that we have, we can say that we want to, instead of apply buzz, we can say that we want to both apply buzz and convert to string, and it's still compile. It will make some tests fail, and you see the result, the resulting behavior is different because I changed the composition of the objects. So this is what we can do with this new declarative way of writing code that we refactored our way to. And that's all for today. Thank you very much, and I hope you liked it.